Okay, kids, we're back here. I got a couple of questions for 3U, Chapter 1, Assignment Question 7. So it says a ferry boat is crossing a river that's 850 meters wide. So look, there's the river, 850 meters wide. The shore here is in green, so shore is one of the reference frame. Here's the water moving in the river, so water is one of the reference frame. Okay, and here's the boat, and the boat is in the water, and that's one of the reference frames. So we have our three reference frames: boat, water, shore. And the average velocity of the water relative to the shore is 3.8 meters per second east. So velocity of the water with respect to the shore is 3.8 meters per second east. This would also be known as current. And the average velocity of the boat relative to the water is 4.9 meters per second south. So that's telling you that this boat is always pointing south as it's moving in the water. So it's aiming south. All of its engine power is pushing in the water while the water is moving, yes, but it's pushing through the water. So if you were to look at it with respect to the water, it's just moving south with respect to the water. And then it says, determine the velocity of the ferry boat with relative to the shore. So the velocity of the boat with respect to the shore, VBS. So this is the BS velocity. So now that's going to equal the velocity of the boat with respect to the water plus the velocity of the water with respect to the shore. Remember the rule I told you? If B is first, B has to be first here. S shore was last, it has to be the last one. And then you have to find some other reference frame that links them. So even if you get confused in a question and you remember this, you'll end up getting the right answer, even though in your gut, I think you understand that the velocity of the boat with respect to shore is going to equal the fact that the boat is moving in the water while the water is moving. And we know this information, so we can write that down, and that would equal 4.9 meters per second south plus 3.8 meters per second east. So it's telling you that from the person here on the shore watching all this happen, it's telling you that they're going to see the boat move to the south and move to the east both at the same time. So it's not going to get directly across the river. All right. So if we want to do vector tip to tail addition for these, velocity of the boat with respect to the water, right? There's that. Velocity of the boat with respect to the water, there she be. And then vector tip to tail. So here's the tip. I'm going to add the tail of the other vector, velocity water with respect to the shore. Here is the sum, the addition of adding these two vectors, which would be velocity of the boat with respect to the shore. So basically, I've shown a graphical representation of this equation right here. What does it mean to add these two vectors? It means you add them like this: vector tip to tail addition. Here is your answer. So the person on the shore sees the boat. It's still going to be aimed this way, right? The boat doesn't change the direction. So all along the motion, the boat is still aiming south, but as it's being aimed south, it gets its way across the river and also moves downriver. So a little bit of each. Now, we want to describe the magnitude of velocity boat to shore and its direction, right? So we want the magnitude of boat to shore. That's what we want there. And that's Pythagoras, right? The boat to shore ends up being the hypotenuse of a right angle triangle. There's the right angle. So that would be 4.9 meters per second squared plus 3.8 meters per second squared. You add those squares, then you find the square root of that addition, and you get your answer. So this gives us 6.2 meters per second. That's just the magnitude of that. Now we want to find the angle. Now, I don't care what the textbook does. We find the angle here. That's the way we do it. So the angle would be theta is equal to tan inverse of the opposite side all over the adjacent side, which would be tan inverse. The opposite is 3.8 meters per second. The adjacent is 4.9 meters per second. And that'll give us 38 degrees. Okay, so that means velocity of the boat with respect to shore is equal to 6.2 meters per second, 38 degrees east of south. So there it is. We're comparing it to the black line here, right? Because this angle is between a known direction south and the direction we're trying to describe here in purple. So you shifted away from the south in an easterly direction by 38 degrees east to south. Now, I've gotten a bunch of kids wondering about, oh, the textbook's different. Look, kids, let me explain something to you. It's all about complementary angles, okay? All about complementary angles. Oop, I wanted that in a different color. Let's see if I can do that. There we go. So there is your 6.2 meters per second, 38 degrees east of south. So there's your 38 degrees. But the complement to that is here, which is 52 degrees. So you could rewrite this as 6.2 meters per second, 52 degrees south of east. And I'd be okay with that. Either one is fine. Let's not get too hung up on this. All right, either one is fine. So that's A. B says, look, you're crossing this river, right? You're going to get from one side of the river to the other side of the river, right? And depending on what the current is, your path will be different. If there's no current, let's say someone dams up the river, you go straight across. If it's a slow current, yeah, you'll get across and maybe you'll end up down the creek a little bit, end up down the river a little bit. If it's a fast current, right? If it's a fast current, whoa, you'll end up way down the river. Okay? Here's the interesting thing about it, and if you watch some of the videos that I've been posting about this, the fact is that the time to get across the river is the same in all of these situations because the engines are always pushing across the river. And the boat is being pushed to the east by the current. So the current doesn't interfere with the push of the engines because they're perpendicular to each other. So whatever time you calculate for no current to get across the river, slow current to get across the river, or fast current to get across the river, it's going to be the same answer. So why not do it in the simplest way? No current. Why would I do that? Because I know this is 850 meters to go straight across. I know that. I don't know what this would be when there's a slow current. I could calculate it or what this would be when there's a fast current, but that would require another calculation. I know straight across is 850 meters. So this is a situation where there is no current. So current is not involved. So it's just the velocity of the boat, right? Velocity of the boat with respect to the water. There's no current, right? Is equal to the distance. Let me turn that into a velocity instead of a speed instead of a velocity. The distance is the distance across the water. And how much time does it take? Well, we know that just pushing yourself through the water is 4.9 meters per second. I'm not even going to worry about direction here. There's no current. So let's keep this really simple. That's 850 meters. And that's your equation with the substitution. And you want to calculate this. So your time just becomes 850 meters divided by 4.9 meters per second. All right. So we're going to calculate that. So this is 173 seconds, give or take. Well, how did I get seconds out of that? Well, look, I got meters in the denominator and meters per second excuse me, meters in the numerator, meters per second in the denominator. Multiplying by a fraction is the same as multiplying, so excuse me, dividing by a fraction is the same as multiplying by the inverse. So dividing by a fraction is the same as multiplying by the inverse. You learned that in math class. So look, cancels, you got seconds. So it takes 173 seconds to get across the river in any situation. In any situation. So next, determine the displacement of the boat as it crosses from the north shore to the south shore. Now we're going back to the real life situation. We actually have a situation where there is a current. So when the current is 3.8 meters per second east, what's the displacement here? Well, look. Oops, I want another color here. Right? The velocity of the boat with respect to the shore is equal to the displacement that the boat moves through with respect to the shore divided by how much time it took. I want to find this value right here. So I need to rearrange this equation, and I get displacement of the boat with respect to the shore is equal to the velocity of the boat with respect to the shore, all times how much time it took to get across. Well, kids, this you got from part B. You know that. This you got from part A. You know that. And remember, it's a vector. Do not forget that you're multiplying a vector by a scalar to get another vector. So your final answer must definitely be a vector in order to calculate this. All right. So there's a little situation there that we made a quick little video for. And I hope you'll have a lovely day. Bye-bye.